Welcome back to Lecture 4 in our series on AI in Railways and System Assurance. Over the first 3 lectures, we have built up a pretty solid foundation. We started in Lecture 1 by looking at what AI is actually doing in the rail industry today and the unique assurance challenges it brings to the table. In Lecture 2, we tackled the big guns, the Synelec RAMS framework, and worked out how to apply it to AI. Then, in Lecture 3, we moved into the newer landscape of AI-specific standards from the EU AI Act and ISO 42001 to the practical toolkits from the RSSB. But now, it's time to bring it all together. In this lecture, we are moving away from the abstract theory and diving deep into 3 concrete AI applications that are currently transforming maintenance and engineering. First, we'll look at machine vision inspection. This is about using AI to spot defects in rails, wheels, catenary systems, and signaling equipment before they become a problem. Second, we'll explore predictive maintenance. We'll see how we can use sensor data to actually predict component failures before they even occur. And third, we'll look at digital twins combined with reinforcement learning. This is the next level of maintenance, using AI to optimize entire maintenance schedules across vast stretches of infrastructure. For each of these, we aren't just looking at the cool tech. We're going to ask the tough questions. What are the RAM's implications? What are the key assurance challenges? And most importantly, how do the standards we discussed in the previous lectures apply to these specific cases? By the end of this session, you'll have a practical, hands-on understanding of how to design, assure, and deploy AI in rail maintenance, all grounded in real-world examples and the rigorous standards we have spent our time learning. You might be wondering, why are we spending an entire lecture focusing on maintenance? Well, it really comes down to 2 big reasons: economics and safety. First, let's talk about the economic side. Maintenance is one of the biggest cost drivers in the rail industry. Historically, we have relied on 2 main approaches, and both have their flaws. On one hand, you have preventive maintenance, where we inspect or replace parts on a fixed schedule, say every 5 years, regardless of whether that part is actually worn out. It's safe, but it's incredibly wasteful. On the other hand, you have corrective maintenance, which is essentially fixing it when it breaks. This is reactive. It leads to emergency repairs, massive delays, and major service disruptions. AI-powered predictive maintenance is what finds the sweet spot. It allows us to detect degradation early enough to intervene before a failure occurs, which minimizes both the cost and the disruption. And we are seeing real results here. Railways that have deployed these systems are reporting a 20 to 30% reduction in maintenance costs, longer lifespans for their components, and significantly fewer unplanned possessions. But beyond the money, there's safety. We know that maintenance failures are a leading cause of rail incidents. By using AI for early detection, we can stop a failure from ever reaching a critical threshold. That's why operators are investing so heavily in this. It's that rare win-win where you improve efficiency and safety at the same time. In this session, we're going to look at 3 different technical approaches to making this happen, and as you'll see, each one brings its own unique set of RAMs and assurance implications. Our first technical approach is machine vision inspection. Essentially, this is about using AI to automatically detect defects by looking at images or video. Here's how the setup typically works. We mount high-resolution cameras, sometimes standard RGB, sometimes thermal, onto an inspection vehicle or even a passenger train. As that vehicle moves along the track, even at speeds over 100 kilometers per hour, it's capturing a constant stream of data. That data is then fed into an AI model, usually a deep neural network, that's been trained to know what a defect looks like. And the range of what these systems can detect is honestly impressive. On the rail surface, they can spot everything from tiny cracks and material loss to corroded fasteners or gauge deviations. They can monitor wheels and axles for flat spots, check catenary wires for wear or fouling objects, and even keep an eye on signaling visibility or vegetation growth. It even works for level crossing surface degradation. The advantages here are clear. First, there's the speed. A manual inspection team might cover 20 kilometers on a good day. This system can cover over 300 kilometers at full track speed. Then there's consistency. AI doesn't get tired, it doesn't get distracted, and its results are reproducible. And in terms of accuracy, we're seeing deep learning hit over 95% for many defect types, which often matches or even beats a human inspector. However, this is where the assurance challenges start to creep in. Because these systems are so data dependent, their accuracy is only as good as the images they were trained on. If you haven't shown the model enough corner cases like rare defects or unusual weather, the performance can drop off a cliff. We also have to worry about distributional shift. A model trained perfectly on standard gauge rails in the UK might fail completely if you move it to a different rail type or gauge. Then you have edge cases like weird shadows or reflections that can fool the model. And finally, there's the interpretability problem. When the AI flags a section of track, it's often a black box. It can be very hard to debug exactly why it made that choice. But don't worry, as we move through this lecture, we are going to cover the specific assurance strategies to tackle every single one of those challenges. Now, let's look at the first pillar of RAMs, reliability. In this context, we are talking about the system's ability to do its job without failing. On the positive side, AI vision systems can be a massive boost for reliability. They can spot early-stage defects, things like hairline cracks in the rails, tiny flat spots on a wheel, or even slightly corroded fasteners that a human inspector might miss or that are just too subtle to see on a single pass. By catching these issues weeks or even months before they reach a critical threshold, maintenance teams actually have the luxury of time. They can plan and execute repairs during scheduled downtime, which means fewer surprises and fewer unexpected in-service failures. But this reliability isn't guaranteed. We face three major technical hurdles. The first is misclassification. This is the classic false negatives, where the AI model looks at a cracking rail and says it's healthy. If the inspection misses that defect, a failure will eventually happen in service. This usually happens because the training data wasn't diverse enough or because the model wasn't tested against enough real-world messy scenarios. To assure this, we need rigorous validation on data that actually represents the real world, combined with constant accuracy monitoring. The second challenge is distributional shift. Imagine a model that was trained perfectly for standard gauge tracks in the UK. If you take that same model and deploy it on a network with different rail profiles or fastener types, its performance can drop unexpectedly. The solution here is a core concept we have mentioned before, the operational design domain or ODD. You have to explicitly define the exact conditions where that model is valid, and you must test it on data from the new domain before you trust it. Finally, there is model drift. Over months of operation, the world changes. New rail types are introduced, weathering patterns shift, or even the camera calibration itself might drift. If nobody is watching, the model's accuracy can slowly degrade until suddenly you see a spike in failures. This is why our assurance strategy must include continuous monitoring, clear triggers for when to retrain the model, and always a layer of human oversight. So, the big RAMs takeaway here: to keep reliability high, you have to validate extensively before you go live, define your ODD clearly, and never stop monitoring once you're in operation. Next, we have availability. In the real world, this is all about how much of the time our tracks and trains are actually open for business. On the positive side, AI is an absolute game changer for availability because it removes the human labor bottleneck. Think about it. A traditional manual inspection team might cover 100 kilometers in a week if they're lucky, but an AI vision system, it can run 24/7 on unmanned vehicles at full mainline speeds. A single system can cover over 300 kilometers in a day. Because you can inspect the entire network so much more frequently, you catch degradation early. This translates directly into more time for planned maintenance, fewer emergency interventions, and ultimately better availability of your trains. However, there are some specific availability killers we have to design against. First, there's the risk of a single point of failure. If you rely entirely on one AI system or one set of cameras and that system goes down, your entire inspection capability collapses. You can't let your maintenance strategy be that fragile. You need redundancy, multiple inspection vehicles, and a clear, graceful degradation plan, like having fallback schedules for manual inspection if the tech fails. Second, and this is a big one, is the problem of false positives. If your AI is oversensitive and starts flagging shadows as critical cracks, your maintenance teams are going to waste thousands of hours investigating non-issues. This is the efficiency paradox. If the AI is too noisy, it actually reduces availability by consuming all your maintenance bandwidth on ghost problems. Finally, don't overlook the computational bottleneck. If you're processing images in the field, on the vehicle itself, your computing power is limited. But if you rely on the cloud, you are at the mercy of network latency or cloud outages. A smart mitigation here is a hybrid architecture. Let the vehicle do a quick and dirty flag in the field and then do the heavy detailed analysis back at the office. So, the Rams takeaway for availability: design your system to fail gracefully. You have to tune your thresholds to minimize those false positives, because even if you miss a few minor defects, it's often better than completely overwhelming your maintenance teams with bad data. The third pillar is maintainability. In our world, this isn't just about how easy it is to fix the AI, it's about how easily our technicians can understand and act on what the AI is telling them. When it's done right, a vision system is a maintenance crew's best friend. It doesn't just shout defect here and leave them guessing. It provides a full brief, the exact GPS coordinates, the specific rail, the type of defect, and even the estimated severity. It can even tell them, I'm 95% sure this is a crack and you need to inspect it within 2 weeks. This allows crews to show up to a possession with the right tools and the right materials already in hand. They can prioritize the high severity items first and plan their work sequence perfectly. The result? Faster repairs, shorter possessions, and a much more maintainable network. But we have to be careful not to create a trust gap. The biggest hurdle here is the black box problem. Deep neural networks are notoriously opaque. If the model flags a critical defect but can't explain why, a technician looking at the image might see a bounding box but still feel unsure if it's a real emergency or just a weird reflection. To fix this, we need to use explainability tools, things like SHAP or LIME, that actually highlight which features in the image triggered the alert. We need to give them confidence intervals, not just a single number. Then we have the issue of false alarms. They have talked about how these kill availability, but they also kill maintainability. If a crew gets sent out to investigate a critical crack 3 times in a row only to find it was just a shadow, they are going to stop trusting the system. They'll either start ignoring the AI entirely or waste time doing their own manual checks every single time. This is why we must tune our decision thresholds based on real operational feedback from the people on the ground. Finally, watch out for data pipeline fragility. If the image noise filtering fails or the data gets corrupted during processing, the technician ends up acting on garbage. We need automated data quality checks and full logging of every transformation the data goes through. The Rams takeaway here is simple: prioritize transparency. If the technicians don't understand or trust the AI's recommendations, the system has failed. We have to monitor that human-AI interaction and be ready to update our models based on what the crews are telling us. Finally, we reach the most important pillar of all: safety. In our industry, safety is defined by the absence of unmitigated hazards. The positive impact of AI here is massive. We know that rail defects are the primary precursors to accidents. A tiny crack in a rail is just a derailment waiting to happen if it propagates undetected. By catching these issues early, AI vision is literally preventing accidents before they can even start. It also means we can handle these repairs during planned, controlled maintenance sessions, rather than in the high pressure, high risk environment of an emergency trackside repair. But because the stakes are so high, the safety challenges are where we have to be the most rigorous. The absolute nightmare scenario is the false negative. This is when the model fails to see a critical crack. The defect keeps growing, invisible to the system, until it eventually leads to a derailment. This is the most critical failure mode we face. To mitigate this, we can't just be happy with high sensitivity in a lab. We have to verify that true positive rate in the field. We might use multiple inspection passes or require a human expert to review every flagged section. We must always have a fallback manual inspection schedule as a safety net. Then there's the issue of misidentified severity. If the AI calls a minor scratch critical, we might trigger an emergency diversion that actually increases overall network risk by creating chaos. Conversely, if it undergrades a true emergency, we have failed our primary mission. Our mitigation here has to be a robust validation of how the AI classifies severity, and we must always allow a human crew to override the AI if their on-site judgment differs. Finally, we have to guard against automation bias. This is a psychological risk where crews start to overtrust the machine. Imagine a technician who looks at a crack and thinks, "Wow, that looks deep," but then sees the AI gave it a low risk score and decides to defer to the computer. That is a failure of the system. We prevent this through training that emphasizes human judgment and a user interface that explicitly encourages verification rather than blind acceptance. The RAM's takeaway here is non-negotiable. Safety is the overriding constraint. Achieving 95% sensitivity on a test dataset is a great start, but you have to prove it works when the rain is pouring and the track is dirty. You have to define your operational design domain clearly and have rock-solid fallback mechanisms for every high-risk decision. Now that we understand the RAM's implications, let's actually apply the Senelec framework we learned in Lecture 2 to this machine vision system. This is how you move from a cool AI project to a certified rail system. We start with EN50126, the RAM's lifecycle. In the early concept and design phases, we have to make a fundamental strategic choice. Is this AI going to replace human inspection to save costs, or is it just going to supplement it to improve safety? That choice dictates everything: the rigor of your assurance and how you allocate your RAM's requirements. Moving into phases 3 through 5, the heavy lifting of design and validation happens. You don't just train a model, you specify exactly what goes in, like high-res RGB images, and exactly what comes out, like a bounding box with a confidence score. You have to source your training data from a massive diversity of track types, climates, and rail ages. And then comes the validation. You don't just look at a spreadsheet, you run an operational trial. You deploy it on, say, a 50-kilometer test section for 3 months and manually verify every single prediction the AI makes. You listen to the technicians. Do they trust it, or are they suffering from alert fatigue? Next, we look at EN50128, which governs our software process. Here, we translate our HARA into hard requirements. For example, the model must detect cracks 10 millimeters or larger with at least 95% sensitivity. Or, the false positive rate must be under 2% to avoid overwhelming the teams. We also set a fallback requirement. If the model's confidence is below 0.7, it must automatically flag that section for a human pair of eyes. Everything from the version of PyTorch you use to the specific version of your training dataset must be under strict configuration management. If you update the model, you retest, you review the safety case, and you follow the change control process. Finally, we pull it all together into the EN50129 safety case. Your safety claim is bold but specific. This system reduces the risk of undetected rail defects to an acceptable level. You identify your nightmare hazard, the missed crack leading to a derailment, and you assess it. Since a derailment is catastrophic, your risk controls have to be rock solid. You point to your 97% test sensitivity as evidence. You point to your 3-month operational trial, but you also acknowledge the limits. You define your operational design domain. This is valid for UK standard gauge mainline track and only for rail types A, B, and C. If you want to move it to a broad gauge network or different rail profiles, you state clearly that revalidation is required. By the end of this process, your assurance argument is complete. You have shown that between the AI's high sensitivity, the annual manual fallback inspections, and the weekly accuracy monitoring, the risk is officially under control. This is how you turn black box AI into a transparent, defensible safety system. To give you a sense of how this looks in the real world, we can look at major operators like Deutsche Bahn in Germany or Network Rail in the UK. These organizations aren't just experimenting with machine vision anymore, they're deploying it at scale. When you look at these systems in action, the capabilities are impressive. They're mounted on regular passenger trains or dedicated high-speed vehicles, allowing them to inspect an entire national network in a matter of weeks, a task that used to take months of manual labor. The system automatically categorizes every defect by type and severity, geotags it with precise GPS coordinates, and feeds it directly into a reporting dashboard. A technician doesn't have to hunt for problems anymore. They just open their screen and see a prioritized list of exactly where to go and what tools to bring. In terms of performance, these systems are hitting 95 to 98% accuracy. More importantly, they have managed to keep the false positive rate between 1 and 2%. That's the magic number where you avoid that dreaded alert fatigue. And from a business perspective, the math works out. A system like this often pays for itself in just 2 to 3 years through labor savings and by catching small problems before they turn into expensive emergencies. But it hasn't been a perfectly smooth ride. Operators have observed some very specific challenges in the field. Weather sensitivity is a big one. In heavy rain, thick fog, or snow, the performance can drop, and some operators actually have to pause inspections until the weather clears. We have also seen sunlight reflections on the rail trigger false alarms, essentially blinding the AI with a glare that looks like a crack. There's also the ongoing challenge of severity estimation. It's one thing to see a crack, it's another to accurately estimate its depth or the volume of material loss just from a 2D image. And of course, there's the issue of new defect types. If a new pattern of corrosion emerges that wasn't in the original training set, the model might sail right past it. So, how do these operators handle assurance in practice? They don't just set it and forget it. They typically take a 5% random sample of the AI's predictions every month and have a human expert verify them. If there's a discrepancy, they investigate, did the AI get it wrong or did the human? They also commit to quarterly retraining sessions to make sure the model is constantly learning from new environmental variations and any new failure modes that have cropped up. This is what a living, breathing safety system looks like. It's a constant loop of detection, verification, and improvement. Our second application is predictive maintenance. If machine vision is about looking for trouble, predictive maintenance is about listening for it. We use condition monitoring sensors, things like vibration, temperature, and acoustics, to catch the subtle signs of a component failing long before it actually gives up. The setup is quite different from cameras. Here, we are installing sensors directly onto the critical hardware, rolling element bearings, wheels, gearboxes, and even the rails themselves. These sensors are constantly recording vibration signatures and temperature spikes, streaming that data to a machine learning model. The model's job is to extract features from that noise and predict what we call the remaining useful life, or rule. The reason this works so effectively is that mechanical failures almost always follow a predictable degradation pattern. In the early phase, everything seems normal to the naked eye, but the sensors pick up subtle vibration increases. In the middle phase, that degradation starts to accelerate. You'll see vibration spikes and heat building up. By the time you hit the critical phase, the component is screaming. You have rapid vibration and imminent failure. By monitoring for those early phase indicators, we can schedule a repair long before the situation becomes an emergency. Take wheel bearings as a real-world example. We use something called WILD, Wheel Impact Load Detectors, at the trackside. These measure the shock every time a wheel passes over. Our historical data shows us that if a wheel has a shock signature exceeding a certain threshold, there's a 95% probability it will fail within 30 days. Instead of waiting for a breakdown on the main line, the maintenance team simply schedules a replacement during the next planned possession. The advantages are massive. You extend the lifespan of your parts because you aren't replacing them on a rigid, arbitrary schedule. You prevent in-service failures, and you save about 20 to 30% on your overall maintenance spend. But from an assurance perspective, this introduces some new headaches. First, there's data quality. Sensors live in a harsh environment. They can degrade or produce garbage as data, and bad data leads to bad predictions. Then there's the training problem. To train a model to recognize a failure, you need examples of components actually failing. But for high safety critical parts, we try really hard not to let them fail, so we often lack the data we need. We also have to deal with uncertainty. An AI might say a part has 10 days of life left, but what's the confidence interval? Is it 10 days plus or minus 2 or plus or minus 8? And finally, we have distributional shift. A model that works perfectly for a wheel from supplier A prime might be completely wrong for supplier B because of different materials or manufacturing tolerances. As we did with machine vision, we're going to look at how to build an assurance strategy that manages these uncertainties. Now, let's look at how this predictive approach shifts our RAM's balance. It's a bit of a tug of war between high-tech efficiency and real-world uncertainty. First, let's talk about reliability. On the positive side, we are catching degradation in its infancy. Fewer unexpected failures mean a much more reliable service. However, we have a major blind spot: new failure modes. If the model was trained on historical data, it's essentially looking at the past. If a new wear pattern emerges because of a heat wave or a change in track geometry, the model might not recognize it as a threat. The component fails and the system is caught off guard. To mitigate this, we have to commit to continuous learning, feeding every single unexpected failure back into the model to keep it evolving. Next is availability. The big win here is extending component lifespans. Instead of pulling a wheel set every 5 years just because the calendar says so, we keep it running until it actually needs help. But the availability killer here is the false positive. If the model screams that a bearing will fail in 14 days, but it's actually healthy, you've just pulled a perfectly good train out of service for no reason. If you have a 10% false positive rate across a fleet of 100 bearings, that has 10 unnecessary interventions a year. To manage this, we have to tune our decision thresholds. We might raise our intervention trigger from 70% to 85%. It's a delicate balance. You reduce the false alarms, but you have to accept a slightly higher risk of a true failure slipping through. That brings us to maintainability. This is where the AI becomes truly actionable. A technician gets a clear brief. Bearing A on axle 5 is degrading. You have about 21 days. This makes maintenance predictable. But we also have to deal with uncertainty. If the model says 21 days, plus or minus 7, do you wait until day 25 or do you act on day 14? This uncertainty gap can lead to distrust if the technicians don't understand the why behind the numbers. Our mitigation here is transparency. We shouldn't just give a date, we should show the features, like a 40% jump in vibration, and train our teams on how to interpret those confidence intervals. Finally, the most critical pillar, safety. The benefit is obvious. You're stopping catastrophic failures, like an axle breakage, before they can cost lives. But the danger is overconfidence. If a maintenance team starts believing the AI is infallible, they might start skipping their manual walkarounds. If the model has even a 5% miss rate, that's 5% too many for a safety critical system. The RAM's takeaway here is that human judgment must remain in the loop. We mandate secondary checks for high-risk components. If the AI predicts a failure, the technician doesn't just swap the part blindly, they perform a visual confirmation first. In the safety world, the AI is an advisor, but the human is the authority. Now, let's get into the paperwork that keeps the trains on the tracks. We are going to walk through the technical audit for our bearing failure system using the same standards we applied to the vision systems. First, we look at EN 50126 and our hazard identification. We have two main hazards here. The first is the nightmare scenario. The AI misses a bearing degradation and we have a catastrophic axle breakage in service. The second is the efficiency hazard, a false alarm that triggers an unnecessary emergency repair. When we assess the risk, the missed failure is high risk because it's hard to control once it happens. The false alarm is medium risk because while it's annoying and expensive, a technician can usually verify the bearing before they start taking the train apart. To control these risks, we set strict boundaries. For hazard 1, we mandate a sensitivity of over 95%, backed up by weekly monitoring and an annual manual inspection of 5% of the fleet, just to catch anything the AI might have missed. We also define a strict operational design domain. This model might be a genius at predicting failures on freight trains for classes 66 through 68, but we declare it invalid for passenger stock or different bearing manufacturers until it's specifically revalidated. Next, we move to EN 50128 for the software development. Here, we translate those safety needs into engineering requirements. We aren't just running a script, we are using a gradient boosted model that looks at vibration, temperature, and shock loads. Our validation process is rigorous. We test it on 1200 bearing recordings, and then we move to a 3-month operational trial at a single depot. We don't just look at the numbers, we talk to the technicians. If the AI says a bearing is failing, does that prediction actually make sense to the person looking at the hardware? Finally, we wrap everything into the EN 50129 safety case. Your safety claim is your promise. This system reduces the risk of in-service failure to an acceptable level. Your evidence is your paper trail. The validation reports showing 95% sensitivity, the logs from your operational trial, and the fact that during that trial, you had 0 failures of bearings that the AI had marked as healthy. But remember the restrictions. A safety case is only as good as its boundaries. If the sensors are damaged, or if the train is operating outside its standard profile, the safety case tells us to flag the data as invalid. By following this process, we move from guessing when a bearing might fail to having a defensible, certified system that we can trust with lives and cargo. Finally, we reach the cutting edge of rail maintenance, digital twins combined with reinforcement learning, or RL. If machine vision is the eyes and sensors are the ears, this is the brain that optimizes the entire maintenance strategy. A digital twin is a high-fidelity virtual model of a physical track section. It mirrors everything: the rail profile, the ballast condition, even the local weather patterns. Because this twin is synchronized with real-time sensor data, it doesn't just show us what the track looks like now, it uses a degradation model to show us what it will look like in the future. This is where the reinforcement learning agent comes in. Think of the RL agent as a strategist in a simulation. It tries out different actions like replace sleepers now versus wait 6 months, and it receives rewards based on the outcomes. If it prevents a failure while keeping costs low, it gets a high score. If it lets a track defect develop, it gets a penalty. Over thousands of simulations, the RL agent learns an optimal maintenance policy that a human might never even consider. For example, it might discover that on a specific heavy freight line, replacing sleepers slightly more often actually allows you to reballast less often, saving 15% in total costs while reducing incidents by over 60%. It's about moving away from one-size-fits-all schedules and toward a strategy that is perfectly tailored to every individual mile of track. However, while this is incredibly powerful, it introduces some of our toughest assurance challenges yet. First, there's the sim-to-real gap. An RL agent might find a quirky solution that works perfectly in the virtual world but fails miserably when it hits the messy reality of physical steel and stone. Then there's the risk of reward hacking. If we don't design the scorecard perfectly, the agent might find a loophole. For instance, if we tell it to 19 minimize maintenance costs without a strong enough penalty for risk, the agent might decide the 19 optimal strategy is to never do maintenance at all. We also have the interpretability problem again. RL policies are often driven by complex neural networks. When the agent says, replace these sleepers today, and a senior engineer asks why, the agent can't always give a human-readable answer. And finally, we have to deal with hard safety constraints. In a simulation, the agent can fail 1,000 times to learn a lesson. In the real world, we have zero tolerance for that. We have to ensure that the RL agent respects safety limits as absolute, unbreakable laws, even if violating them would save a fortune. As we wrap up this lecture, we'll see how to wrap these intelligence strategies in a safety framework that keeps the RL agent on the right side of the tracks. When we apply RAMs to something as complex as a digital twin with reinforcement learning, we have to change our perspective. We are not just looking for a bug in the code, we are looking for a flaw in the AI's logic. Let's start with reliability. The core risk here is the sim to real gap. An RL agent learns by trial and error inside a simulation. But what if the simulation, the digital twin's degradation model, is fundamentally wrong? If the model thinks the track is sturdier than it actually is, the policy it learns will fail in the real world. To assure this, we don't just trust the simulation. We validate the digital twin against 2 or 3 years of actual historical data to ensure the virtual degradation matches the physical reality. Before we ever deploy a policy, we run it against another year of unseen historical data to see if the AI's recommendations would have actually worked. Next is availability. An RL agent is a cost optimizer by nature. If left to its own devices, it might try to under-maintain, skipping a repair here or there to save a few dollars, while accepting a higher failure rate than we are comfortable with. To prevent this, we don't just give the AI a goal, we give it hard constraints. We bake an absolute limit into its reward system. For example, the failure rate must never exceed 0.5%. If the AI proposes a policy that breaks that rule, it's rejected automatically. Finally, we have the ultimate pillar, safety. If the RL agent makes a poor strategic call, we could be looking at a cascade of failures that lead to a major incident. To prevent this, we use a heavy penalty system in the training. We tell the AI that a safety failure is essentially an infinite loss, a 1,000,000-point penalty that it must avoid at all costs. But even with those penalties, we never let the AI have the final word. In the safety world, the RL agent is a high-level advisor. Every major maintenance change it suggests must be reviewed and approved by a human engineer. We monitor the actual failure rates in real time, and if they even start to deviate from what the AI predicted, we have a kill switch to roll back to our proven traditional maintenance schedules. The RAM's takeaway here is that while the AI can find the optimal path, human-defined safety boundaries are what keep that path from going off a cliff. To see how this looks in practice, we can look at a European railway operator that recently deployed an RL-based system on a 200-kilometer heavy freight corridor. They didn't just turn it on. They started by feeding 3 years of historical data, track geometry, maintenance logs, and incident reports into their digital twin. Once they had a degradation model that could predict reality with 85% accuracy, they let the RL agent loose in that virtual environment. The agent's goal was clear: find a policy that balances the cost of actions like sleeper replacement and reballasting against the reward of preventing failures. But the most important part was the safety constraint. The failure rate could never exceed 0.5% per year. The results were fascinating. The RL agent actually suggested different strategies for different sections of the track. For the heavy freight Class A press sections, it recommended replacing sleepers more often than the traditional 3-year cycle, every 2.3 years, while slightly extending the reballasting intervals. Naturally, the engineering teams were skeptical. Why replace sleepers sooner, they asked. But when they ran a 12-month pilot on a 50-kilometer section, the data spoke for itself. Compared to the traditional schedule used on an adjacent stretch of track, the pilot section saw 21% fewer maintenance activities and a staggering 67% reduction in defects. Most importantly, the failure rate dropped to 0.3%, well below the safety limit. But the real lesson from this deployment wasn't just about the math, It was about the assurance in practice. The operator established a strict monthly monitoring cycle. If the failure rate ever ticked toward that zero point 0.5 limit, they had a protocol to investigate and adjust the policy immediately. They also committed to an annual deep dive where the model is retrained with the latest data and the updated policy is validated offline before being pushed to the field. The three big takeaways here. First, your digital twin is your foundation. If your model is wrong, your AI will be wrong. Second, RL policies are often non-intuitive. You have to be prepared for the AI to suggest strategies that go against decades of common sense, which is why the simulation phase is so vital. And finally, human buy-in is everything. You can have the smartest algorithm in the world, but if the maintenance crews don't understand and trust the new schedule, the system will fail on the ground. By combining the innovation of RL with the rigor of Senelec standards, this operator didn't just save 15% on costs, they built a more resilient, safer railway. We have covered a lot of ground today, looking at three very different ways AI is transforming rail maintenance. To wrap things up, let's look at how they stack up against each other so you can decide which tool is right for which job. Think of machine vision inspection as your foundation. Its primary purpose is to catch what is already there, the visible cracks, spalls, and wear. Its greatest strength is its speed and objectivity. It completely removes the human bottleneck from the inspection process. From an assurance standpoint, your focus is on the operational design domain, making sure the camera sees correctly in rain, snow, or tunnels. This is a commercially mature technology, and it's usually the best place for an operator to start if they want to improve reliability and speed up diagnosis. Next, we have predictive maintenance. This moves us from seeing to forecasting. By using sensors to monitor vibrations and heat, we can predict when a part is going to fail. This is the biggest driver for availability because it turns emergency repairs into planned interventions. The assurance challenge here is managing uncertainty. You need to know not just that a bearing is failing, but how confident the AI is in that timeline. This technology is maturing rapidly, especially for high-value components like wheels and gearboxes. Finally, we have the brain of the operation. Digital twins plus reinforcement learning. This is about high-level strategy. It looks at the whole network holistically to find non-obvious ways to save money while staying safe. The assurance focus here is the most complex. You have to bridge the sim to real gap and ensure the AI respects your hard safety constraints. While this is still in the early to mid commercial stages, it offers the highest potential for cost savings and long-term efficiency. So, how do you decide where to invest? Start with machine vision if your biggest bottleneck is currently the frequency or accuracy of your manual inspections. Layer in predictive maintenance for your high-value assets where a sudden failure causes massive disruption, like bearings or traction motors. Invest in digital twins and RL once you have a solid foundation of historical data and the engineering expertise to manage a high-fidelity simulation. Each of these approaches has a unique RAMS profile, but when combined, they create a railway that is not just automated, but truly intelligent, safer, more reliable, and significantly more efficient. To wrap up our technical session, we need to talk about EN 50716. Think of this as the essential update to the software standards we have used for years. It was created specifically because the industry realized that traditional software rules aren't enough when you're dealing with the unpredictability of machine learning. The biggest shift here is in data governance. Under this standard, data is no longer just a resource, it is a safety-critical artifact. This means you have to document every data source and prove its quality. Is it complete? Is it accurate? Is it free from bias? You must have total traceability, meaning you can prove exactly which images or sensor readings were used to train a specific version of your model. Then there is the requirement for reproducibility. In the past, AI was often seen as a bit of black magic, where you throw data at a model and hope for the best. EN 50716 ends that. You are now required to document your training procedures so thoroughly, including fixed random seeds and specific software versions, that another team could take your code and data and recreate your exact model. No more unexplained successes. When it comes to operation, The standard mandates strict model governance. You have to establish clear KPIs like sensitivity and false positive rates and monitor them constantly. But more importantly, you must have predefined triggers. You don't just wait for a failure to happen. You decide ahead of time that if your accuracy drops by, say, 5%, you automatically trigger an investigation or a model rollback. Every update is subject to the same rigorous change control as any other part of the signaling system. Finally, the standard pushes for explainability. It acknowledges that while we might never have perfect transparency with a deep neural network, we must strive for reasonable transparency. We use tools like SHAP or Line to help operators understand why the AI flagged a specific weld or predicted a bearing failure. In short, EN 50716 takes the Wild West of AI and brings it into the disciplined world of rail engineering. It ensures that as we move toward these intelligent systems, we never lose sight of the documentation, reproducibility, and transparency that have kept our railways safe for over a century. As we conclude Lecture 4, I want you to look at this matrix not as a list of separate features, but as a single, integrated ecosystem. When we talk about smart rail, we aren't just talking about replacing a person with a camera. We are talking about a system where machine vision feeds the eyes of the operator, predictive sensors provide the heartbeat of the hardware, and digital twins act as the strategist that brings it all together. But remember, the intelligence in artificial intelligence is only half the story. The other half is the assurance framework. Whether you are using a simple image classifier or a complex reinforcement learning agent, your job as a RAMS engineer remains the same. Define your boundaries, the operational design domain, verify your data, the EN 50716 standard, keep the human in the loop, the safety case. By applying these rigorous Senelec standards to these new technologies, we aren't just making the railway faster or cheaper, we are making it fundamentally more resilient. We are building a system that doesn't just wait for things to break, but understands how to keep them running safely for the long haul. Thank you for your time today. In our next lecture, we'll move from the trackside to the train itself, looking at AI in signaling and autonomous train operations. To conclude our deep dive into Lecture 4, I want to leave you with a clear 6-step blueprint. This is how a maintenance AI project moves from an idea in a meeting room to a certified system on the track. Think of this as the integrated framework that pulls every standard we have discussed into a single, cohesive workflow. Step 1. Define the problem through EN 526. We don't start with the AI, we start with the HARA. We identify the hazards like undetected rail cracks or bearing failures, and we set our RAMS targets. Only once we know what safe looks like do we decide if AI is the right tool to get us there. Step 2. Choose your AI approach. Based on that HARA, you select your weapon. Is it machine vision to break an inspection bottleneck, predictive maintenance to catch degradation, or a digital twin with RL to optimize the entire strategy? Your choice here dictates your data needs and your validation complexity. Step 3. Govern development with EN 528 and EN 50716. This is where the engineering happens. You translate your safety needs into technical requirements, model accuracy, the boundaries of your ODD, and your fallback behaviors. You treat your training data as a safety-critical artifact, documenting every source, versioning every model, and ensuring that your results are reproducible. Step 4. Establish organizational governance with ISO 42001. While the engineering team builds the model, the organization builds the safety net. You establish your data management policies, your monitoring triggers, and clearly define who is responsible for the model at every stage of its life cycle. This ensures the AI has a structured home within the company. Step 5. Build the safety case with EN 50129. Now, you pull your evidence together. You structure an assurance argument that proves your model's 95% sensitivity combined with your human-in-the-loop overrides makes the system safe. You document your ODD and your monitoring plan in a technical safety report. This is your license to operate. Step 6. Deploy, operate, and evolve. The work doesn't end at deployment. You enter a phase of continuous monitoring. You track your KPIs, accuracy, latency, and false positive rates weekly or monthly. If you see performance drift, you investigate, you gather feedback from the maintenance crews, and you retrain the model. As new evidence emerges from the field, you update your safety case to reflect reality. By following this 6-step path, we ensure that AI isn't a black box mystery, but a disciplined, transparent, and, most importantly, verifiable part of the railway's future. Thank you for joining me for Lecture 4. You are now equipped with the technical and regulatory knowledge to lead the next generation of smart rail maintenance. I'll see you in Lecture 5, where we'll explore AI in the world of signaling and autonomous operations. We have looked at the standards and the technology, but now let's look at the calendar. If you were tasked with leading a maintenance AI project starting tomorrow, what would the next year of your life look like? Here is your 12-month roadmap for a successful deployment. Phase 1, assessment and planning. Months 1 to 2, you don't start in a lab, you start in the maintenance shed. You meet with the teams to find the real bottlenecks. Is it inspection speed, scheduling, or cost? You identify a few candidate AI solutions and run a feasibility study. You're looking for the sweet spot where clean historical data meets a high return on investment. By the end of month 2, you have made your choice. You know exactly which AI approach you're pursuing. Phase 2, data preparation and model development. Months 3 to 6, this is the heavy lifting phase. You gather your historical records and sensor logs, then clean them, handling the outliers and the missing values that haunt real-world data. You train multiple algorithms, tuning hyperparameters until you find the best performer. Most importantly, you verify that model on a test set, data it has never seen before, and document every single step of the process. Phase 3, safety case and approval. Months 7 to 9, this is where you align with the CNELEC standards. You conduct your HERA to identify specific hazards and map them to controls like your ODD and fallback procedures. You draft your EN 50129 safety case and your technical safety report. This phase involves intense internal reviews and, if necessary, regulatory submissions under frameworks like the EU AI Act. You don't leave this phase without a formal approval to operate. Phase 4, pilot deployment, months 10 to 12. Now, the rubber meets the road. You install the system in a limited scope, perhaps 50 kilometers of track or 5% of the fleet. You train the staff on how to use it and, more importantly, how not to over-rely on it. You monitor performance daily, comparing AI predictions to actual outcomes. By month 12, you have the data to prove the system works and the user confidence to back it up. Phase 5, rollout and continuous improvement. Year 2 and beyond. Once the pilot is a success, you scale to the full network. But you don't set it and forget it. You establish weekly accuracy tracking and a governance procedure for model updates. This is the continuous improvement phase, where every mile of operational data makes your AI smarter and your railway safer. This 12-month journey is how we move AI from a promising experiment to a certified standard. It requires discipline, transparency, and a relentless focus on safety. But for those who follow this roadmap, the rewards, higher availability, lower costs, and zero unexpected failures are well worth the effort. As we close out today's session, I want to leave you with 5 definitive takeaways. These are the principles that will distinguish a successful, safety-certified AI deployment from a failed experiment. First, machine vision is ready for duty. It is mature, scalable, and deployable right now. If your railway is struggling with inspection bottlenecks or human error in visual checks, this is your starting point. Just remember, its power is only as good as its operational design domain. You must be clear about exactly where and when it can see reliably. Second, predictive maintenance is about managing uncertainty. By listening to the heartbeat of your bearings and gearboxes, you can prevent failures before they happen and extend the life of your hardware. But never forget that every prediction comes with a confidence interval. Your job is to catch the failures while keeping the noise of false alarms low enough that your technicians still trust the system. Third, digital twins and RL are the strategists. They offer the highest potential for holistic network optimization, finding the non-obvious paths to efficiency that humans might miss. However, they are high maturity tools. You must have a rock-solid digital twin and ironclad safety constraints in your reinforcement learning model to ensure the pursuit of efficiency never compromises the pursuit of safety. Fourth, let RAMs be your North Star. Reliability, availability, maintainability, and safety are not just boxes to check, they are your design guide. Use RAMs thinking at the very beginning of your project. Ask yourself, what will this system improve? And what new risks does it introduce? If you can answer those questions, your path to certification will be much smoother. Fifth, use the full framework. From the HARA in EN 50126 to the AI-specific rules in EN 50716 and finally to the ISO 42001 governance, these standards are your protection. They provide the structure to deploy AI systematically, safely, and transparently. If there is one thing I want you to remember from today, it's this. AI for maintenance is not a plug-and-play technology. It is a sophisticated engineering discipline. It requires thoughtful design, rigorous validation, and continuous monitoring. But for those willing to do the work, the payoff is undeniable. A 30% reduction in costs, a 60% improvement in failure detection, and a railway that is safer than ever before. Thank you for your attention. I'll see you in Lecture 5, where we take these same principles and apply them to the high-stakes world of signaling and autonomous train operations. Before we part ways today, I want to leave you with 3 questions to help you reflect on your own specific context. Whether you are managing a freight corridor or a high-speed passenger line, your AI journey starts with these reflections. First, what is your biggest maintenance headache? Be honest about where the pain is. If your teams are overwhelmed just trying to keep up with visual inspections, then machine vision is your immediate answer. If you're tired of seeing bearings fail on the main line and disrupting the schedule, then you need to focus on predictive maintenance. And if you feel like you have the data but your scheduling is still inefficient, then it's time to talk about digital twins. Second, do you actually have the data to support that choice? AI is only as good as the fuel you feed it. For machine vision, can you start collecting high-quality images of defects during your current manual checks? For predictive maintenance, do you have at least a year of sensor data tied to actual failure records in your CMMS? And for digital twins, do you have the 2 to 3 years of degradation history required to build a faithful model? Third, what does a safe pilot look like for you? The biggest mistake you can make is trying to boil the ocean on day one. Don't try to automate the whole network. Pick a 50-kilometer stretch or 5% of your rolling stock. Prove the concept, build the confidence of your technicians, and then scale. As we look ahead, in Lecture 5, we're going to shift gears from maintenance engineering to operations and traffic management. We'll see how AI is moving from the maintenance shed to the control room, transforming how we actually move trains across the network. And finally, in Lecture 6, we will tackle the most human part of this journey, ethics and human factors. We'll explore the critical considerations for deploying AI in an industry that, at its heart, will always be safety critical and human dependent. Thank you for your attention today. Take these questions back to your teams, and I'll see you in the next lecture.
All right, that's it for this session. If you found this helpful, hit the subscribe button and turn on notifications so you don't miss the next one. And quick reminder, make sure you check out the podcast series here on the channel, Rams Ready for Everything Rams, and Safe Tracks for System Safety Assurance. If you're following along with this course, those episodes will really help connect the dots. Thanks for watching and stay tuned for the next one.